Hi, I'm Andrew, and this is part 12 in the Advent of Code series where every day I'm attempting to solve a new code challenge. Previous videos are on a playlist on my channel called Advent of Code 2022, and if I'm able to solve any challenge for the day, the code that I write will be uploaded to my public repo. The link for that is in the description of this video, so for today, let's get started with part 12. This is the hill climbing algorithm. You try contacting the elves using their handheld device, but the river you're following must be too low to get a decent signal. You ask the device for a height map of the surrounding area, which is our puzzle input. The height map shows the local area from above broken into a grid. The elevation of each square of the grid is given by a single lowercase letter, where A is the lowest elevation, B is the next lowest, and so on up to the highest elevation, which is Z. Also included on the height map are marks for your current position, which is an uppercase S, and the location that should get the best signal, which is an uppercase E. Your current position, S, has elevation A. The location that we would be at the end with the best signal is elevation Z. So we need to go from the lowest point up to the highest point. You'd like to reach E, but to save energy, you should do it in as few steps as possible. So during each step, you can move exactly one square up, down, left, or right. To avoid needing to get out of your climbing gear, the elevation of the destination square can be at most one higher than the elevation of your current square. That is, if your current elevation is M, you can only step up to N, but not to O. Okay, so that also means that the elevation of the destination square could be much lower, so you can jump down, you just can't jump up. For this example, we would start at the top left, and then the end would be somewhere over here. Our goal is to get here with the least number of steps. You could start by moving down or right. Eventually we'll need to head towards this E. It shows this is the most optimal path. And these directions show which way we went. So in this case, we follow this path all around until we get to the end. And it reaches the goal in 31 steps, which is the fewest possible. So we need to find what is the fewest steps required to move from our current position to the location that we get the best signal. All right, so this uses kind of a path traversal. I don't remember the name of it, but essentially what we have to do is take our starting position, and then we'll have to find, we'll have to look at each direction that we can go and then track what the distance is so far. And then as we keep going, we'll eventually get to the end by using that method. Now, we have to check whether it's a location that we can actually get to, and that'll be whether the height is within one taller. But let's get our puzzle input and start checking. So it looks like this is probably some sort of mountain here. We need to figure out where we start. Oh, looks like over here, but our solution won't have that hard-coded. We'll just need to check because it should work with any input. We'll put that into our editor and then start writing some code. So in order to get this into something that we can work with, I think I'll make a 2D array and just store. I'll have to convert these letters into the height for that square, and then also when we get to the start, it said that we start on an A, so I'll have to keep that in mind. And then the E is going to be a Z. So we'll want to track as we're going through and filling these when we get to an uppercase S or E. We'll want to track that that's our start and end position for our coordinates. So let's go ahead and start that. We're going to make the grid here. It'd be a list of list. I think we're going to want to make a class to model this. It's going to be a list of this one call it a square. There's already a built-in type for that. I will call it a position, and we'll make our own class for that. A position is going to have an X and Y coordinate. Like this, and then we'll need to track the height of it. And then we need to make that a val. So when we go through, and we'll need the distance of these positions, but we won't know that while we're filling up the grid with items. So we'll start with making this distance. We'll just make it nullable and start it as null like this. Okay, so now as we take our input for each, we're going to have a list of lines. And then for lines, we're going to have a list of characters, and each character is going to be a position. So we will need to do this indexed for each of these. Like this, indexed, same here. It will be the index and the, actually we should put this as our coordinates. So this is going to be the y as we go up and down, and then x will be as we go left and right, and then we'll have it like this. Okay, so now for each point, we are going to we're going to update this, and so we can take anytime we get to a new line, we're going to want to add a new grid position. So we can just take we'll do this. We will say grid add, and this needs to be a mutable list. This, and then I think this will also need to be mutable. So we'll add a new mutable list, and then we'll go through and add new positions for each character. So yeah, let's go ahead and do that. We can say we will return into the last grid item, we'll add a new position. X is going to be X, Y is going to be Y, and then the height is going to be, we can convert A through Z to a range. Think like this. Can never remember what the syntax is for this. No, not like that. Okay, right. So we have a list of characters here. So now we're just going to take the index of our character. And that will tell us, and I think, did it say if we started 0 for the index, position A is the lowest elevation. Okay. So I think that works. I think we can just say that A is 0. Okay. And what we'll also need to check is, yeah, because when we get to an uppercase A or an uppercase E, or an uppercase S for start, we'll have to do something different here. So let's say if the character is equal to uppercase S, start, else if we're equal to an uppercase E, then we're end. Otherwise, we can follow this logic here. We'll still need to add a position for those. We'll just do something a little different with it. We will say, oh, we need to set that here of height. We'll do that. So we can just say that height is 0, I guess, and here we would put height as 25. Okay, and we will also want to make a note of our start and end positions. So start position. Just create it like this, and 0. We'll make another one for end. We'll fill these in as we go. Okay, so when we get here, we will say that this is our start position, and then we can actually just put that in here. Start position is going to be X, Y, 0. And here our end position will be this, and we'll add our end position. Okay. I think that's good for now. Yeah, these are redundant, but we're still going to use them in our next bit of logic. So yeah. Now what we're going to want to do is make our logic for looping through each of these, and what I think that we'll need to do for that is and I'm actually going to clean up some of this so it doesn't take up so much space. I'm just going to put these on single lines and get rid of the argument names, and we'll do that. This. Okay, and the same thing here. Because I have a feeling that we'll have a good amount of logic that we don't want it to take up too much space. Okay. Well, there we go. All right, so now what we'll want to do is make a list where we are tracking the current items that we're looking at. So when we start here, we want to just have this very first position. That's all we're checking. And for this, we will check all around it and any items that are 1 or less above this and don't already have a value assigned. That's what we want to add kind of to our next list of items to check, and then we'll go and check those one at a time and kind of just do the same thing as we go. So I'm going to make a current positions, which is a mutable list of position, and then I'm going to have a staged positions. And that will just kind of let us loop through, check all the ones that we need to check, add their touching positions, and then once we finish looking through all the current positions, we'll move the staged into this. So really what we'll want to do is say probably while current positions is not empty. Yeah, or actually we'll say while staged positions is not empty, and we'll start with saying that staged positions is going to be beginning with start position. Great. And as soon as we start this loop, we will take current positions and add all of stage positions, and then stage positions we will clear. And then what we'll do from there is look through all of our stage positions like this and say we will add stage positions based on whether we have one we can touch. Now the only thing that's tricky about this is we need to so when we're checking up here in the top left, we won't be able to move up or to the left because we're at an edge. So that's just what we'll need to check is what the available positions are. And in fact, we can even probably make some, maybe make it a function to check that. So given our current position, we could just take we can take the grid. We could take the size, so we could take the height and the width, and that's how we know if we can go if we're at an edge or not. So on position, we'll make a function for that, and we'll say we'll want to make it so that we can get all of the other positions that it's touching. So we could say get other positions, and it'll return a list of position. But if we do that, it's going to need the list of all positions. So positions, is it our grid? We could pass it the grid like this. And we'll say positions for each staged positions, add all, and we'll pass in the grid. And this needs to return a mutable list. Stage positions, we have a mutable list of starting positions, so what is this? Oh, we're adding all of the grid. We need to add all of this, get other positions with the grid. Right. Okay. So this is going to, we already have our own position. So we can say grid width is going to be grid first item, assuming that it's the same, yeah. So we'll say the first size, and grid height is going to be grid size. So this is how many lines are in the grid. And we will say we have a list of other positions, which is a mutable list of position, and we'll return that at the end of our function here. And so this is where we can have the logic to say if it's touching and it's not higher, or not too much higher. So we can say, yeah, so we'll want to check our left, which will be if our x is not 0. Get left. We'll just repeat this for all the different edge cases and say if y is not 0, then we can get top, and if x is not, we want to say grid width, or grid width. Yeah, so we'll get the left, the top, this will be the right, and this will be the bottom for grid height. And actually, I think I have these reversed, because if y is 0, then we're at the bottom left. So if we're at the bottom left, then we can't get the bottom. Yeah, okay. And I'm just going to move this over here so that they're grouped together better. And I might have an off by one thing here, because the grid height is going to be the number of items, so 1. Yeah, I think it should be -1 for these. There we go. So to get the left item, we would say grid, we would get the same y, so that's going to be the first thing here, so we would get our y, and then we would get the x -1, and we can say other positions. We're going to add this one. Oh, but only if the height is within our range. So we're going to say again in here if, we'll just add it up here, if this and no, we'll want to do here because we need to get our other position. So position is going to equal this. We're only going to add it in if it's not too high. So we'll say if other position height, let's see, so we need to get if the other position's height is within 1, is less than or equal our height plus 1. So that's our condition, and if it meets the condition, oh, and we also only want to add it if it's distance and other position distance is null, because with this algorithm, the first time that we get to a position and we set its distance, we know that that's the shortest that it could be. So then if another way gets to that same position, we just want to skip checking it again. So we'll do this. We'll add the other position in this case. Yeah, so far so good. At some point we need to update the distance, so I think we could even do that here. Maybe we could just take that other position distance and set it to, we need to set it to our distance plus 1. And let's see, other distance val, okay, so we need to make these reassignable as a variable. And we can, oh, because this is nullable, we can maybe assert that it's non-null, like that. Yeah, so far so good. I think for our start position, we need to set the distance to 0. Because, yeah, if we start there, then it's always going to be 0. Yeah, like that. Now that could give us issues because if we start with the start position and the stage positions, it is not going to, when we go through this, it's going to add, so I might need to just redo this actually. So current position we'll start with this. And then we'll need to update our logic. So we're only going to do this when current positions is not empty. We'll just kind of put this at the end. So after we do all of this and we have our stage positions, then we will add all. No, I think we need to clear our current positions and then add all from our stage positions. And then clear our stage positions. Yeah, I think that makes sense. So now down in our logic here, we need to just continue doing this for each side. This is going to be getting the right item. It will be x plus 1. Getting the bottom will be y minus 1 and just keeping the x the same. And here it will be y plus 1, keeping the x the same. The rest of the logic should be the same. We can only move in any direction. We can only move if the height is good here. So yeah, this is our full input. I'm going to take our sample input though and just run through that quick to validate. So I'll put that in here and we'll run and see what we get. Oh, okay, and so for end position, yeah. All right, so I'm gonna set a breakpoint kind of at the first time that we finish a loop. Let's see how it goes. Okay, and we got a null pointer exception under here, so we are getting a distance and it is, we're asserting that it's not null, but it is null. So that, when would that happen? That would happen, we're starting with our start position. It has a distance. So our start position shouldn't be null. We are adding, we'll set the breakpoint here maybe. Well, it happens in get other positions. So, yeah, let's check this. Kind of go through one line at a time. So when we get here, we have our current positions. There is a position and distance is null. Distance should not be null. Current position should have the start position. Start position. Oh, right. That's because we assigned the distance up here, but not at this point when we actually created it. Should have caught that. Okay. So now let's redo this. Okay, so when we get here, so far so good. Current positions is 2. So that should be, yep, x is 1 and y is 0, and the reverse. So what that's saying is we started here, and now these two are both available, and their height should both be 1, right? Height should both be 1. And if we have a grid, it's a 5, I think by 5. So 5 high by 1, 2, 3, 4. We should be 8 wide. If we look at that, yep, 5 by 8. Okay, so the first run was good. Let's check the second run. So now we should have, for these two, we should be able to check this one, and this one. And we have 3 items. Current positions. Yeah, so we have 2 to the right, we have 2 above, and that's because this is actually flipped from kind of the perspective we're looking at it, and then 1 and over. So it would be a line like that. Yeah, let's just keep running through it and see if it hits any snags. It looks like it made it all the way through out of our loop, and our grid, these items, yeah, okay, so these items have they have everything filled out. Everything has a distance. Cool. Let's check the position of the end item. End position should be x is 5 and y is 2, so that would be here, and y is 2, that would be this item. I think that would be, no, that's 2 and 4. What was I looking at? End position is an x of 5 and y of 2. End position x5, y2. So that would be the fifth item. Oh, right. So y is 2 here, and x is 5. Okay, so 31 is the distance. What did it say in our example? 31 steps. Oh, okay. So maybe we're there. Let's get our real input back in there and rerun our program. Oh, and I didn't return anything. So what I should do is return, I need to take our grid then and find so end position, we're gonna get end position y for the first list, and then end position x for the second, and then I'm going to get the distance. And what is that saying? We found question mark because distance starts out as null, but I think we would know that by this point it should not be null. So we're going to run this and see what it gets. It says 420 is the shortest distance. Let's give it a shot. And that's the correct answer. Awesome. So moving on to part 2, let's see what it has us do. As you walk up the hill, you suspect that the elves want to turn this into a hiking trail. The beginning isn't very scenic though. Perhaps you can find a better starting point. So to maximize exercise while hiking, the trail should start as low as possible with elevation A. The goal is still the square marked E. However, the trail should still be direct, taking the fewest steps to reach its goal. So you'll need to find the shortest path from any square at elevation A to the square marked E. Okay, again, consider the example from above. We were starting here, but now there's 6 choices for our starting position. We could start at any of these lowercase a's. Okay. So there's 5 that are marked A plus the S here. Where's the other A? Oh, there we go. It's at the bottom. So these 4 plus that one. If you start at the bottom left square, you can reach the goal the most quickly. So down here. Okay. This path reaches the goal in only 29 steps, the fewest possible. All right. Yeah, so now it's really the same thing. We just have to choose the best starting position. So let's think about how we could do that. So my first idea is to go over and just check each starting position. There's quite a few lowercase a's, but if we look at this, there is just over 1,000, so maybe it won't be too bad to just check each one. There's probably a smarter way to do it, but if this just gets us the answer, then I'm good with that. So let's copy over part 1 into part 2 and just go from there. The only difference here is going to be that we try multiple starting positions. We are going to put a list of results. We have a list of integers that's going to represent the shortest path, and we can put that right here. And what we'll do is after each check, we'll add a new result list. So yeah, we will need to get the starting position of each lowercase a. So really by this point we have a grid with all the heights. It's not the letters anymore. So we'll have to look through the grid and find, we'll have to have a list of starting positions. Let's say starting positions. We have a list of position. And we will have to take the grid. Well, yeah, this will be a little tricky because we're updating the grid distances, so we would have to kind of reinitialize this multiple times. Yeah, and that's fine. So yeah, we'll just do that. We'll go back through the grid and just reset the distances to 0. Actually, the distance is to null except for our starting position. So in this point, we can kind of ignore what it says the starting position is. We can instead just treat it like any of the other ones. So we'll just do that logic there. Yep, okay. Now we will want to take our starting positions for each, kind of do this. At the end of these, we'll want our result list up here as well. The rest of this logic is going to happen inside of here, where the result list is going to add what we were returning for part 1. So like this, and then down here we will just return the result list, the largest item, so max. So now inside of this list, what we'll do, first we need to fill out our starting positions, and we can just say here if the character is A, or if the character is an uppercase S. then it's going to be a starting position that we can consider. So we'll do it like that. Starting positions will need to be a list up here, and we'll probably just replace it like that. And we could say starting positions, add a position like this, where x is our x, y is our y, height is 0, and distance is 0. Okay. And now under here, we will want to name this like position, and that's where we will start our list with. Okay. Then what we'll need to do is kind of reset all of this after each run, because when we go through this, it's going to adjust everything. So now we will go back and reset things. So we would take grid for each, and then say for each. So this will take every single position. We'll name these list, actually a row. This is a row. Like that. And then this will be a position. We're name shadowing now, so we'll just get rid of that. And so we'll say it distance is going to be reset to null. Yeah, that's fine. The only thing is that our starting positions would then be null, so we can just leave those as null, and whenever we start checking a starting position, we'll set its position distance to 0. And that should cover that case. All right, so essentially what this should be doing is just going through every possible starting position and running the same check. Let's debug that with our sample data and see what the result comes through. And we have an out of bounds index 55. Where are we getting that? Get other positions. We shouldn't be able to do that. It's under part 2 here. Okay, I'm going to debug and see how many times that has happened. So we should get here, and then our first position, we should have our grid. Oh, and we've got all sorts of items here. These shouldn't be different. Oh, and that is because we're not adding that end position, so we should say, right. So we'll just say it's maybe a start, and we're still going to do this, and we're just going to make it a starting position variable. So I could have probably just left what was here before, like this. Starting positions, we're going to add that starting position, and then here we are also going to do that. All right, now let's try it. When I rerun and debug, we shouldn't have an issue there. Okay. And now we got a null. Okay. So our grid at this point is good. It has fixed size, fixed width. The end position. Oh, you know what? I wonder if some can't even get to the end position. That's what I bet it would be. If we say the grids in position by y position, or by x by y. Yeah, I bet. Well, here the distance is 418. So I wonder what the problem is. Or maybe it's just at some point that happens, yeah. So here, yeah, the distance is null. So that means it wasn't able to reach it after exhausting all the paths. So we will just check. We'll assign the distance value. And if it is not null, then we'll add it to our list. We'll do this if distance null. Actually, we could just take it like so. And we'll just add it to our list if it's not null. All right. Now let's debug and see what we get. Okay, so we hit here. There are 218 values out of the over 1,000 starting positions. Only so many of these we're able to get there. Oh, and I think we want to take the minimum because this will take the longest route, right? So if I finish running this, yeah, it'll be 437 is the longest. We want to take the minimum. Again, I'm going to use our sample data. And what did it say was the shortest? 29 steps. And there we go, 29. Okay, so I think that'll work. 414. All right, and we got the second part. So yeah, cool. Yeah, it was good to actually use that algorithm. I forget what it's called, but it's for searching, and I've never had a reason to use it. I've just seen it before, so yeah, pretty cool. I'll just follow up back tomorrow with another video. Thanks for watching.